Welcome to an introduction to partial derivatives. Let's start by considering first a function of a single variable f of x. When we consider a function such as f of x, there is a single independent variable, in this case x. And so the function values change as the x value changes. So in this function, as I change the input x to the function, the corresponding output variables or y variables change. So, for example, if f of x equaled x cubed minus x, which is the graph of this function here, how might we interpret the quantity f prime at 1? So f prime at 1, the input to the function is x, so we're talking about an x value of 1. So here is 1 on the x-axis, and we can see that our function crosses the x-axis at 1, and we can also see there is a tangent line there to the function at 1. So a common interpretation that we give to f prime at 1 is it is the rate of change in the y values as the x values change at that particular point. Also, we can interpret it as being the slope of the tangent line when x is equal to 1. But let's go back and think about this rate of change, because in Calculus 3, in multivariable calculus, we really don't deal with slopes. So let's think more with the context of rate of change. So f prime at 1 is the rate of change in this function with respect to x when x is equal to 1. Now let's consider a multivariable function. In this case, we've got a function f of x and y, where we have two independent variables. So the output of the function f of x and y changes as both the x input and the y input change. So you can see with this graph of our function here on the right that the output variable, or the point on this surface, changes dependent upon the input variables, dependent on what the x value and the y value that are being input into the function are. So it is natural for us to consider rates of change, but there's not a single variable at this point. We now have a function of two variables, so it would make sense or seem natural to consider rates of change with respect to each variable. So for example, I could consider what is the rate of change at this point in the direction parallel to the x-axis, or in the x direction. I could also consider what is the rate of change in the function in the direction of the y-axis, or in the y direction. So with a function of two variables, x and y, there are two natural directions that we might want to consider for rates of change. Now, before we talk about these first order partial derivatives, I do want to remind you that back in Calculus 1, we have the definition for the derivative of a function as being the limit as delta x approaches 0 of x plus delta x minus f of x all divided by delta x. In essence, what we were doing is looking at the rate of change in the function f as we increased x by a small amount delta x. So you're going to notice here that these definitions of the partial derivatives are quite similar to that of what we saw in Calc 1. Now, first of all, we have here is the partial derivative of f with respect to x. And these are two common notations that we use for that partial derivative. Now, this first notation is similar to what you saw in single variable calculus or calculus 1, the notation that was df over dx. It's analogous to that type of notation. This f with the subscript x, you can think of as being similar to the notation where you wrote f prime of x. Notice though that you cannot now write f prime of x for a function of two variables. For if I simply do f prime, I will not know which of the two variables I'm referring the derivative is. So the derivative, the partial derivative with respect to x, is the limit as delta x goes to 0 of f of x plus delta x comma y minus f of x and y over delta x. Notice the similarity to the definition from calculus 1. Notice that we're allowing x to change incrementally based on this limit, and we're not allowing the y variable to change at all. The y variable remains constant. It does not change. We're not incrementally changing that. So we're looking at the rate of change of our function as I incrementally change the x variable. Now, notice that we have this partial derivative of f with respect to y. And notice that in this case, we are incrementally changing the y variable. So we have y plus delta y, and we're letting that delta y go to 0, so it's getting smaller and smaller and smaller. So we're incrementally changing y, and we're not allowing the x variable to change at all. We're keeping the x variable constant, and we're interested in what is the rate of change of the function if we incrementally change the y variable. So these are our first two first order partial derivatives. Now, fortunately, all of the rules for differentiation that you knew and learned in Calculus 1 remain valid. So the power rule, the product rule, the chain rule, the quotient rule, all of those rules are valid, and we use them to find partial derivatives. Now, notice that this function g has two independent variables, u and v, and we want to find the first partial derivatives. So there will be the partial derivative of g with respect to u, and there will be a partial derivative of g with respect to v. Now, recall that when we define these partial derivatives, when I'm doing this partial derivative with respect to u, we treat the other variable as a constant. So we're going to treat v as a constant in this case. And so we're going to, and I'm going to be a little explicit about this so that we're very clear. So we're going to take the partial with respect to u, so I'm going to take the derivative of u squared with respect to u minus the partial with respect to u of 2uv, let me make sure that looks like a 2, plus the partial with respect to u of v squared. Now keep in mind we're treating u as a, we're treating v as a constant. So when I take the derivative with respect to u of u squared, I'm using the power rule, and I'll simply get 2u minus, now I'm taking the derivative with respect to u, the partial derivative, of 2u times v. So I'm going to treat both the 2 and the v. They are both considered constants in the world of partial derivatives. So I'm going to have a 2v, that's my constant, and then now I'm going to take the derivative of u with respect to u. The derivative of u with respect to u is 1. Plus, This last term is v squared, so the derivative of v squared with respect to u. Remember, we're treating v as a constant, so that's going to be 0. So our derivative here, our partial derivative of g with respect to u, is 2u minus 2v. So we've found the rate of change of this function g with respect to u. Now let's find the rate of change of this function g with respect to v. So this time we're going to treat u as a constant because we're interested in the rate of change with respect to v. So any occurrence of u in the function is treated as though it were a constant. So we're going to have the partial with respect to v of u squared minus the partial with respect to v of 2uv plus the partial with respect to v squared. Well, notice that in this first term, we're taking the partial derivative of u squared, but we're interested in rate of change with respect to v, so that's going to be a 0 plus, or I'm sorry, minus. Now we're interested in partial derivative with respect to v, so this 2 will be a constant, and so will this u. So I'm going to have my constant 2u, and then I'm left to take the partial derivative with respect to v of v, and that is 1, plus, and now the partial derivative with respect to v of v squared. Well, that's going to be 2v. So our partial derivative with respect to v of the function g is negative 2u plus 2v. Now, we were able to find second derivatives of functions back in Calculus 1. Well, we can do the same thing with multivariable calculus and multivariable functions, but we have to attend to what those original partial derivatives were respect to. So these are our second order partial derivatives. And so if I should happen to start with a partial derivative with respect to x, I have that original function. There are two partial derivatives that I could take. This function partial of f with respect to x is a function of x and y. So I can take a second partial derivative with respect to x again, or I could start with that partial derivative with respect to x, and I could then take a partial derivative with respect to y. Now, the notation here would be, this is the second partial derivative of the function f, and it's with respect to x both times. This second one, alternatively, over here, if I use the subscript notation, the first partial derivative with respect to x, and then I took another partial derivative again with respect to x, so it's x the first time, x the second time. This notation says that I'm going to start with the partial with respect to x, but then I'm going to apply the partial derivative with respect to y. So I started with the partial derivative with respect to x, and then I applied a partial derivative with respect to y. Notice the order there. I started with a partial derivative with respect to x, and then applied a partial derivative with respect to y. This notation goes from right to left. Whereas with the subscript notation, I started with a partial derivative with respect to x, and then I applied a partial derivative with respect to y. So the subscript notation goes from left to right. So similarly over here, I could just as well have started with a partial derivative with respect to y. That will be a function of x and y. And I could continue to take partial derivatives. So I could apply a partial derivative with respect to x. That would give me a second partial derivative of the function. The first partial derivative was respect to y. The second partial derivative was respect to x. So notice that order goes from right to left. Whereas over here with the subscript notation, I started with a partial derivative with respect to y, and then applied a partial derivative with respect to x. And lastly, here we're taking the partial derivative with respect to y twice. We can write that as the second partial derivative of f with respect to y 2 times, both times. And over here on the right, with the subscript notation, I started with a partial derivative of y, and then I applied the partial derivative of y. So this notation on the left goes from right to left as you apply additional partial derivatives, whereas the subscript notation starts from the left and goes to the right as you apply additional partial derivatives. So now let's find the second partial derivatives of this function g. There will be 4 of them. We start first, order doesn't matter, but we will start first with the partial derivative of g with respect to u. And keep in mind that this creates a function of u and v. And we saw already that this was 2u minus 2v. And now we have that piece of information, so we want the second partial derivative of g with respect to u both times. So that means I'm going to take this 2u minus 2v, and I'm going to apply the partial derivative with respect to u again. And that's going to give me 2. And then we can have the second partial derivative of g with respect to u the first time, and then with respect to v the second time. So that means I'm going to take this original 2u minus 2v, and I'm going to apply the partial derivative with respect to v. Now if I do that, I'm keeping u constant. I'm interested in tracking the behavior of the variable v, so I end up with a negative 2 as that partial derivative. So for each first partial derivative of a function of 2 independent variables, there are 2 second partial derivatives. So then our partial derivative of g with respect to v, again, it was still a function of u and v, was equal to negative 2u plus 2v. And so we could be interested in what's the second partial derivative of g with respect to v both times. Well, then I would take the partial with respect to v of negative 2u plus 2v. Keep in mind we treat u like a constant, so this first term, if I take the partial derivative, is constant. Its derivative is then 0. And then I end up with 2 times the partial derivative of v with respect to v, or 2 times 1. And then I could have the second partial of g, the first time being with respect to v, and the second partial derivative being with respect to u. That would mean we're applying the partial derivative with respect to u to this negative 2u plus 2v. Now, our partial derivative is with respect to u, so we treat this v as a constant. This 2v is a constant, and so its partial derivative of a constant is 0. So I'm focused on the partial derivative of negative 2u with respect to u, so that's going to give me a negative 2. I hope you find this helpful.